Welcome to GCP Load Balancing. Welcome to the channel. I would appreciate it if you would subscribe. I produce videos daily covering AWS, Azure, and GCP also. Hit the notification bell to get notified of new videos. Welcome everyone to this comprehensive guide on Google Cloud Platform load balancing. I am excited to take you through one of the most crucial aspects of cloud infrastructure. How to build scalable, resilient load balancing solutions that can handle millions of requests. In my years of working with GCP, I have seen how proper load balancing can transform an application's performance and reliability. Today, we will cover everything from the fundamental concepts to advanced configurations that you can implement immediately in your projects. We will start by understanding the complete architecture, then dive deep into each component, backend services, URL maps, forwarding rules, health checks, firewall configuration, and scaling strategies. By the end, you will have a complete understanding of how to build production-ready load balancers on GCP. What makes this session special is that we will use real G-Cloud commands throughout. You will not just learn theory. You will see exactly how to implement these solutions step by step. The complete GCP load balancing ecosystem. Before we dive into individual components, let me show you the big picture. This diagram represents the complete load balancing ecosystem in GCP, and understanding this flow is crucial for everything we'll discuss today. Starting from the client request, traffic flows through several key components. The forwarding rule provides the external IP that clients connect to. This is literally the front door of your load balancer. The target proxy handles protocol termination, SSL certificates, and connection management. The URL map is the traffic director. It examines each request and decides which backend service should handle it based on host headers, URL paths, and other criteria. Backend services manage the actual load balancing logic, health checking, and traffic distribution to your compute instances. What's important to understand is that each component has a specific role, and they work together as a cohesive system. You can't just create a backend service and expect traffic to flow. You need the complete chain configured properly. We'll explore each of these components in detail, showing you exactly how to configure them and how they interact with each other. Understanding load balancer types. GCP offers different types of load balancers, each optimized for specific use cases. Choosing the right type is crucial because it affects performance, cost, and functionality. External HTTP/HTTPS load balancers are your go-to for internet-facing applications. They operate globally, provide SSL termination, and offer advanced routing capabilities. These are perfect for web applications, APIs, and any service that needs to serve users worldwide. Internal load balancers are designed for traffic within your VPC. They are perfect for microservices communication, database load balancing, and any internal traffic that doesn't need internet access. They provide better security and lower latency for internal communications. Network load balancers handle TCP and UDP traffic at layer 4. They are ideal for high-performance scenarios where you need to preserve client IP addresses or handle non-HTTP protocols. Think gaming servers, database connections, or custom protocols. The key is matching the load balancer type to your specific requirements. We will show you exactly when to use each type and how to configure them properly. Backend services, the heart of load balancing. Backend services are where the magic happens. They define how traffic gets distributed to your actual compute instances, and getting this configuration right is critical for performance and reliability. One crucial point that often confuses people: creating a backend service alone does not create a load balancer. It's just one component that needs to be connected to URL maps, target proxies, and forwarding rules to function. The load balancing scheme determines the scope and behavior of your load balancer. External managed creates global HTTP/HTTPS load balancers for internet traffic. Internal managed creates regional load balancers for internal traffic. Internal creates Layer 4 load balancers for TCP/UDP traffic. Load balancing methods control how requests are distributed. Round robin spreads traffic evenly. Rate-based balancing considers requests per second capacity. CPU utilization balancing adjusts based on server load, and connection-based balancing manages concurrent connections. We'll walk through configuring each of these options with real examples you can use in your own projects. Backend Service Configuration Deep Dive. Let's get practical with backend service configuration. The balancing mode you choose fundamentally changes how traffic flows to your instances, so understanding these options is crucial. Utilization mode works best with managed instance groups that have autoscaling enabled. The load balancer monitors CPU utilization and automatically triggers scaling when utilization exceeds your target. This creates a self-healing, self-scaling system. Rate mode gives you precise control over requests per second. You specify exactly how many requests each instance can handle, and the load balancer enforces those limits. This is perfect for APIs where you know the capacity of your backends. Connection mode is specialized for long-lived connections. Instead of counting requests, it counts concurrent connections. This is ideal for database proxies, WebSocket servers, or any service that maintains persistent connections. The capacity scaler is a powerful feature that lets you temporarily reduce or increase a backend's capacity without changing the underlying configuration. Set it to 0.1 for gradual rollouts, 0.0 to drain traffic, or 1.0 for full capacity. Session affinity and traffic patterns. Session affinity determines whether requests from the same client always go to the same backend. This decision significantly impacts your application design and user experience. No session affinity is ideal for stateless applications. Each request can go to any healthy backend, providing the best load distribution and fault tolerance. This is the preferred approach for modern microservices architectures. Client IP affinity ensures requests from the same IP address always go to the same backend. It's simple but can cause uneven load distribution, especially when users are behind NAT gateways. Generated cookie affinity uses load balancer managed cookies to maintain sessions. This provides better load distribution than IP affinity while still maintaining session persistence. It's perfect for web applications that need user sessions. The key insight is to design your applications to be as stateless as possible. Use external session stores like Redis or Cloud Memory Store instead of relying on server-side sessions when possible. URL maps are the traffic director. URL maps are the brains of your load balancer. They examine incoming requests and make intelligent routing decisions based on host headers, URI paths, HTTP methods, and even custom headers. The evaluation order is crucial to understand. Host rules are evaluated first. These route based on the domain name in the request. Then route rules are evaluated by priority. These allow complex matching based on headers, query parameters, and other request attributes. Finally, path rules provide simple path-based routing. Path-based routing is incredibly powerful for microservices architectures. You can route /API/star to your API services, /static/star to your CDN, and /admin/star to your admin services, all from a single load balancer. Host-based routing enables multi-tenant applications. API.example.com can go to your API backend, admin.example.com to your admin interface, and www.example.com to your main website, each with their own path routing rules. Advanced features like traffic splitting enable a /B testing and canary deployments. You can send 90% of traffic to your stable version and 10% to your new version, all configured declaratively in the URI map. URL map configuration examples. Let me show you how to implement these URL map concepts with actual G-Cloud commands. We'll start simple and build up complexity. A basic URL map just has a default service. All traffic goes to one backend. This is perfect when you're starting simple or have a monolithic application. Adding path matchers enables microservices routing. The path rules parameter takes comma-separated path equals service pairs. Notice how more specific paths like /API/v1/* can override broader patterns like /API/*. Host rules enable multi-domain routing. You specify which hosts should use which path matcher. This lets you serve different applications from the same load balancer while keeping their routing logic separate. For complex scenarios, you can import URL map configurations from YAML files. This enables features like header matching, query parameter routing, and traffic splitting that aren't available through simple command line flags. The key is to start simple and add complexity as needed. Most applications can get by with basic path routing initially. Forwarding rules. The load balancer entry point. Here is something that surprises many people. Forwarding rules are what actually create your load balancer. Everything else we have discussed, such as backend services, URL maps, and target proxies, are just configuration. The forwarding rule is what instantiates the actual load balancing infrastructure. Forwarding rules provide the external IP address that clients connect to. They specify which ports accept traffic and which target proxy or backend service should handle requests. When you create a forwarding rule, that is when Google actually provisions the load balancer. Load balancing schemes must match across all components. If your backend service uses external_managed, your forwarding rule must also use external_managed. Mismatched schemes will cause configuration errors. Port configuration determines which traffic your load balancer accepts. You can specify single ports like 80, multiple ports like 80 and 443, or port ranges like 8000 to 8010. For proxy load balancers, you typically specify ports explicitly. For pass-through load balancers, you might forward all ports. IP address management is crucial for production systems. Always reserve static IP addresses for production load balancers. This ensures your IP does not change when you modify the load balancer configuration, preventing DNS disruptions. Complete load balancer setup process. Now let's put it all together with a complete end-to-end example. This sequence shows you exactly how to build an external HTTPS load balancer from scratch, and the order matters tremendously. We start with health checks because backend services depend on them. The health check defines how the load balancer determines if your instances are ready to receive traffic. Without healthy backends, your load balancer won't route any traffic. Next, we create the backend service and add our instance groups to it. This defines how traffic gets distributed among your compute instances. The backend service needs to exist before we can reference it in the URL map. The URL map comes next, defining routing rules and referencing our backend service. Target proxies handle protocol termination and SSL certificates. They need to reference the URL map. For HTTPS, we need SSL certificates attached to the target proxy. Finally, the forwarding rule creates the actual load balancer, provides the external IP, and ties everything together. Only when this forwarding rule is created does traffic actually start flowing. This sequence, health check, backend service, URL map, target proxy, forwarding rule, is the foundation of every load balancer in GCP. Health checks, your application's guardian. Health checks are absolutely critical for reliable load balancing. They continuously monitor your applications and make split-second decisions about which servers can handle traffic. I've seen health checks save companies from major outages more times than I can count. The key insight is that health checks operate at two levels. First, they determine which instances are healthy enough to receive traffic. Second, they enable auto-healing in managed instance groups, automatically replacing failed instances. HTTP health checks are the most common. They send GET requests to a specific path and expect a 200 to 299 response code. Design your health check endpoints to actually verify that your application is working, not just return a static OK response. TCP health checks simply verify that a connection can be established. They're perfect for databases and other non-HTTP services. HTTPS health checks add SSL handshake verification. gRPC health checks use the standard gRPC health checking protocol. The timing parameters are crucial. Check interval determines how often health checks run. Timeout specifies how long to wait for a response. Unhealthy threshold is how many failures trigger, marking an instance unhealthy. Healthy threshold is how many successes mark it healthy again. Health check best practices. Let me share some hard-learned lessons about health check implementation. Your health check endpoint should be lightweight but comprehensive. Don't just return OK. Actually verify that your application can serve requests. Check your database connections. Verify that critical dependencies are responding, and ensure your application is truly ready to handle user requests. A health check that passes when your app is broken is worse than no health check at all. Timing is everything. Set your check interval to balance responsiveness with server load. For most applications, 10 to 30 seconds is appropriate. Set timeout to about half your check interval to avoid false positives from slow responses. The unhealthy threshold should be low enough to detect problems quickly but high enough to avoid flapping from temporary network issues. Usually 2 to 3 failed checks is appropriate. The healthy threshold can be lower. Often 1 to 2 successful checks is enough to mark an instance healthy. Remember that health checks come from specific Google IP ranges. 130.211.0.0/22 and 35.191.0.0/16. Your firewall rules must allow traffic from these ranges, or health checks will fail and all your instances will be marked unhealthy. Firewall rules, the security foundation. Firewall rules are absolutely essential for load balancer functionality, yet they're often overlooked until something breaks. Let me be clear. Without proper firewall rules, your load balancer will appear to work in the console but traffic won't reach your backends. Google's load balancers use specific IP ranges that must be allowed through your firewall. 130.211.0.0/22 and 35.191.0.0/16 are used for both load balancer traffic and health checks. If you block these ranges, your load balancer simply won't work. The principle of least privilege applies here. Don't open your instances to the entire internet. Quad 0/0 for backend traffic. Only open them to Google's load balancer ranges. Use network tags to apply firewall rules to specific groups of instances rather than all instances globally. Create separate firewall rules for different purposes. One for load balancer traffic to backends, one for health checks, and optionally one for administrative access. This makes troubleshooting easier and security management more granular. Internal load balancers use different IP ranges. Your VPC's internal ranges like RFC 1918. The same principles apply, but the source ranges are different. Firewall configuration examples. Let me show you exactly how to configure firewall rules for different load balancer types. These commands will save you hours of troubleshooting. For external HTTP/HTTPS load balancers, you need rules allowing traffic from Google's load balancer ranges to your backend instances. The target tags parameter applies the rule only to instances with those specific network tags, following the principle of least privilege. Health check rules are equally important. Even if load balancer traffic is allowed, health checks might be blocked by a different rule. It is often cleaner to create separate rules for health checks and backend traffic. Internal load balancers have different requirements. Instead of Google's external ranges, you allow traffic from your internal networks. The concept is the same, but the IP ranges are different. Always use descriptive names and descriptions for your firewall rules. 6 months from now, you will thank yourself for clear documentation about what each rule does and why it exists. Autoscaling and manual scaling. Scaling is where GCP load balancers really shine. You can build infrastructure that automatically responds to demand, scaling up during traffic spikes and scaling down during quiet periods. This saves money and ensures good performance. Managed instance groups provide automatic scaling based on various metrics. CPU utilization scaling is the most common. When average CPU hits your target threshold, new instances are automatically created. Load balancer utilization scaling responds even faster, scaling based on how busy your load balancer is. Custom metrics scaling lets you scale based on application-specific metrics, like queue length, memory usage, or requests per second. This is powerful for applications where CPU isn't the limiting factor. Scheduled scaling handles predictable traffic patterns. If you know your traffic spikes every morning at 9 a.m., you can pre-scale your infrastructure instead of reacting to the spike. This provides better user experience and cost optimization. Manual scaling gives you immediate control when needed. During unexpected events, or for testing, you can instantly change the number of instances without waiting for auto-scaling triggers. Scaling configuration and best practices. Let me share some practical insights about configuring auto-scaling effectively. The key is finding the right balance between responsiveness and stability. For CPU-based autoscaling, I typically recommend a target of 60 to 70%. This gives you headroom for traffic spikes while keeping costs reasonable. Set your maximum replicas high enough to handle peak load, but not so high that runaway scaling breaks your budget. Cool-down periods prevent oscillation. Without them, you might see instances constantly being added and removed as metrics fluctuate. 90 to 120 seconds is usually appropriate for web applications. Scale-in controls prevent aggressive scale-downs that could hurt user experience. Limit how many instances can be removed at once and require sustained low utilization before scaling down. For predictable workloads, combine scheduled scaling with reactive autoscaling. Pre-scale for known busy periods, then let autoscaling handle unexpected variations. Monitor your scaling events. Set up alerts for scaling actions so you can understand your traffic patterns and tune your scaling policies accordingly. Protocol forwarding handles specialized scenarios where you need to forward specific IP protocols, rather than just HTTP or TCP traffic. This is particularly important for VPN gateways, security appliances, and custom networking solutions. ESP and AH protocol forwarding enables IPsec VPN endpoints. These protocols are essential for site-to-site VPNs and secure tunnels. The forwarding rule directs ESP and AH traffic to your VPN gateway instances. ICMP forwarding is useful for specialized network monitoring tools that need to handle ping and traceroute traffic. While most ICMP traffic is handled automatically by GCP, some applications need direct access to ICMP packets. Custom protocol forwarding supports proprietary protocols by specifying the protocol number directly. This enables support for specialized networking equipment, industrial protocols, and custom applications. Remember that protocol forwarding requires corresponding firewall rules. You must explicitly allow the specific protocols you're forwarding, or traffic will be dropped by the firewall even if forwarding is configured correctly. Advanced load balancing patterns. Let me show you some advanced patterns that solve real-world problems. These techniques can transform how you architect your applications on GCP. Blue-green deployments use multiple backend services with traffic splitting. You deploy your new version to a separate set of instances, test it thoroughly, then switch traffic over instantly. If something goes wrong, you can switch back just as quickly. Canary deployments gradually shift traffic to new versions. Start with 5% of traffic to your new version, monitor for issues, then gradually increase to 10%, 25%, 50%, and finally 100%. This minimizes risk while enabling continuous deployment. Multi-region active-active setups distribute traffic across regions for both performance and disaster recovery. Users get routed to the closest healthy region automatically. If an entire region fails, traffic automatically shifts to healthy regions. Hybrid cloud architectures use Internet NEGs to include external endpoints in your load balancer. You can gradually migrate workloads from on-premises to cloud, or integrate with SaaS providers, all through the same load balancer configuration. Monitoring and troubleshooting. Even the best configured load balancers need monitoring and occasional troubleshooting. Let me share the key metrics and techniques that have saved me countless hours. Load balancer logs show you exactly what's happening with each request, including response times, error rates, which backend served requests, and geographic distribution of users. Enable logging on your backend services and create dashboards for key metrics. Health check monitoring tells you when backends are having problems. Set up alerts for health check failures so you know immediately when instances become unhealthy. The backend services get health command is invaluable for real-time troubleshooting. Auto-scaling metrics show whether your scaling policies are working correctly. Are you scaling up fast enough during traffic spikes? Are you scaling down too aggressively and hurting performance? Monitor scaling events and adjust thresholds based on real data. When troubleshooting, start with the basics. Are health checks passing? Are firewall rules correct? Are backend services configured properly? Most issues come down to these fundamentals. The described commands for each component will show you their current configuration and status. Complete configuration relationships. This comprehensive diagram shows every component we've discussed and how they interconnect. Let me walk you through each element and explain how they work together to create a complete load balancing solution. Client entry point. Everything starts with client requests that go through DNS resolution to reach your static IP address. The static IP is created with G-Cloud Compute addresses create and provides a stable endpoint that doesn't change when you modify your load balancer. Forwarding rules. This is the actual load balancer, created with G-Cloud Compute forwarding rules create. It assigns the external IP, specifies which ports accept traffic, and creates the load balancing infrastructure. This is where traffic enters Google's network. Target proxies. Created with G-Cloud Compute target HTTP proxies create or target HTTPS proxies. These handle SSL termination, protocol management, and certificate attachment. They're the protocol-specific handlers that process incoming connections. SSL certificates. For HTTPS traffic, certificates are created with G-Cloud Compute SSL certificates create. You can use Google-managed certificates that auto-renew, or self-managed certificates for custom requirements. URL maps. The traffic router created with G-Cloud Compute URL maps create. This examines each request and decides which backend service should handle it based on host rules, path matchers, route rules, and default services. It's the intelligent traffic director. Backend services. Created with G-Cloud Compute backend services create. These define the load balancing scheme, session affinity, balancing mode, and capacity management. They're the heart of traffic distribution logic. Health checks. Created with G-Cloud Compute health checks create for HTTP, HTTPS, TCP, or gRPC monitoring. They continuously check application health with configurable intervals, timeouts, and thresholds, enabling auto-healing and traffic routing decisions. Complete configuration relationships. This final diagram shows the complete ecosystem of GCP load balancing components and how they all connect together. This is your roadmap for understanding the relationships between every piece we've discussed today. Starting from the client request, you can see how traffic flows through DNS resolution to your static IP, then through the forwarding rule that creates the actual load balancer. The target proxy handles SSL termination and connects to your URL map for traffic routing decisions. The backend service is where the intelligence lives. It manages load balancing algorithms, session affinity, and capacity scaling. Health checks continuously monitor your applications and feed that information back to the backend service for routing decisions. On the compute side, you have two main paths: managed instance groups for auto-scaling virtual machine workloads, and network endpoint groups for precise endpoint control. Both integrate with the same backend services but serve different use cases. The security layer shows how firewall rules and network tags work together to control access. The specific Google IP ranges must be allowed for load balancer functionality, and network tags provide granular rule application. Notice the alternative protocol forwarding path for specialized traffic like VPN gateways. This bypasses the HTTP/HTTPS stack and goes directly to target instances for raw protocol handling. This diagram is your reference for understanding dependencies and troubleshooting. When something isn't working, trace through these connections to find the issue. Every line represents a configuration dependency that must be correct for the system to function. Thank you for your attendance.